I kind of have an analogy for this, for E student in particular. We learn KCL, KVL. Of course, they're intuitive. You can accept it easily because the river or the water flow to the node must come out if you don't accumulate the charged particle, right? But in principle, KCL, KVL need to prove from Maxwell equation, right? So here is something similar. We're going to analyze the quantum circuits later. And how do we go through this process? Here is just to give you some tools. So I don't expect you to understand the background. But however, some concepts are important. For example, I want you to accept that we do have something called generalized coordinate, right? It's related to the coordinates we see in the real space. A generalized velocity. Later you will find that, generalized coordinate can be the phase of the Josephson junction, right? Generalized momentum can be the charge in your circuit, right? So we have coordinates, we have velocity, and someone, right, came up with something called Lagrangian. They are super smart. We don't need to understand how they came up with this, right? But the point is that you come up with something called Lagrangian, and this Lagrangian has the variable, depends on the coordinates and also the velocity and the time. Once I have this Lagrangian, I can use it to predict how my system will evolve. Right, Q1, Q2 are the coordinates, maybe for particle 1, particle 2, or it can be the if this is vector, right, or it can be the x component, y components, but anyways, all of them, right? The Lagrangian, basically, you can say it is the kinetic energy minus the potential energy. You can see that. So once we have this Lagrangian, what you need to do is just that we have something called Lagrangian equation, or Lagrange equation. That it has this form: partial L partial velocity and then d dt minus partial L partial coordinates equals to 0, right? And for Lagrangian, I also can find out the so-called generalized momentum. And last time I showed you by using this Lagrange equation, we're able to predict the motion of a free particle. We also predict the motion of a simple harmonic oscillator. Remember? Yeah. Similarly, there's another formulation, right? If you are interested, you can dive deep into it. Otherwise, just take it for granted, like how you learn KCL and KVL at that time, right? Hamiltonian, again, is an expression, but instead of express using the coordinates and velocity as the independence variable, it used coordinates and momentum as the independence variable. And remember, I made a mistake last time when I tried to do the Hamiltonian, and then I got the wrong result because I tried to use the velocity in the equation, right? Forgot? Yeah, I thought did something wrong, right? Go to watch the video. And then I correct it in the class, right? Well, I need to use the momentum. So Hamiltonian, usually you say it is the total energy. It is the kinetic energy plus the potential energy. And we usually need to start with the Lagrangian and then use this equation to find out what the Hamiltonian is. It is equals to the summation of the generalized momentum times the velocity minus the Lagrangian, right? And this one I did not mention last time, is how we came up with this Lagrangian Hamiltonian equation. Again, you don't need to know why, but this needs to be on your cheat sheet, or you know that you can search, you can Google, right? Basically, it's just that if the energy conserved, you expect dH dt equals 0, right? Because Hamiltonian is the total energy. Then you just use the train rule, right? This is the train rule. Then it means this whole thing needs to be 0. There are many different choices. One of the choice is to choose this, right? There must be some reason. Again, I'm not deep into this, right? The physics people and math people came up with a good reason why they want to do this. And from here, we find that it has two equations. The rate of change of the momentum equal to negative partial h partial q, which is the coordinates, right? And then the rate of change of the coordinate, which is the velocity, is partial h partial p. Now, so this review did not give you anything. The most important thing is that we have Lagrangian, Hamiltonian, you take it for granted. Each of them has its own independence variable, generalized coordinate and velocity, generalized coordinates and momentum. They can convert to each other through this equation, right? Or maybe say from Lagrangian to Hamiltonian through this equation. And both of them have their own equations, Lagrangian equation and Hamiltonian equation, which we can use to deduce the equation of motion. Right? The rest is just a table. Yeah. Say again? In Maxwell equation, I will show you later. We are going to quantize it, but not Maxwell. We're going to quantize the wave equation. So Lagrangian and Hamiltonian is like, you start with classical mechanics, something we can understand well, but then we go through this generalized coordinates and velocity. Then we will be able to quantize the wave. Right? But I go too far. But even for Hamiltonian, you also have it is the total energy, right? So I think you also have the Hamiltonian for the wave, yeah, in classical.
So you can describe Hamiltonian for just about any mechanical system, quantum system.
Yeah, and Hamiltonian is the linkage between the classical and quantum mechanics. So we are going to, I'm going to show you this is the next slide. We start with a simple harmonic oscillator. We do so-called promotion. We change the x and p, generalized coordinates and generalized momentum, to an operator which does not commute with each other. So we introduce the quantum mechanics to it. And then we will be able to describe the quantum behavior of a simple harmonic oscillator. Right? And this is what we're going to do for our EM wave and also for our circuit. Right? So we'll do that. And we'll keep repeating. Very messy. I'm sorry, because it's first time to teach this class and I'm not good enough. So all I can do is just present you the equation. Maybe Guru can give you more insights, but I need to use the equation to explain what I'm going to say. Right? It will be messy. I hope you can try, but no worry about the final, right? It will be reasonable, but you need to understand my class, okay?